compiling probabilistic programs for variable elimination with information flow. And Jianlin is the speaker for this.
Thanks, Chair. Hello, everyone. This is Jianlin. The paper is about compiling probabilistic programs for variable elimination with information flow. This is work in collaboration with Eric and Yizhou. Probabilistic programming languages are very powerful tools for statistical modeling and inference. Suppose we have a data set that records a person's heart rate, and the problem is to infer whether the person is walking or running. We can solve this problem with probabilistic programming. The program uses a emission distribution to model how heart rate depends on the state of the person. Running leads to higher heart rate. And the program first samples the initial state of the person. It then performs Bayesian conditioning. It conditions the initial state on emitting the observed heart rate. A step distribution models how the state transitions. If a person is currently running, then they are more likely to be running than walking in the next time step. The program samples the next state of the person and conditions this next state on emitting the next observed heart rate. We repeat this many times, and this gives us a hidden mark model. By returning the next state, the inference problem is defined as to predict how likely a person is running at the next time step, given a history of observed heart rates. We can read this hidden mark model much more concisely with recursion. And this recursive function HMM takes the initial state and the history of the observed data as input. It then pattern matches on the data and recursively calls itself. We fed these programs to existing PPLs for exact inference. And these PPLs are designed for such programs. We discovered that for HMM of just length 60, it already takes this PPL like tens of minutes to either compile the program or run the compiled program. In this work, we tackle this problem of scalable inference for such probabilistic programs. We work with an expressive functional language with recursion, which allows easy and concise modeling. And we call this PPL Maple. Our compiler for Maple is able to compile a recursive probabilistic program like HMM into a recursive but pure program by factorization and marginalization. We aim for correct compilation, scalable compilation, and also scalable inference on the compiled program. To start simple, let's think about how we solve the non-recursive version of the HMM. To compute the conditional distribution, we need to compute the joint probability of the observed data and the next state. This joint probability is a marginal probability. It marginalizes out the hidden state variables from Z0 to Zn. The joint probability of all the variables can be written as a sequence of factors. Each factor corresponds to one line in the program. Directly computing the sum over all variables is expensive, and the inner product contains n+1 free variables. So computing the sum amounts to enumerating all possible assignments to the latent variables and computing a probability table of an exponential number of rows. So enumeration-based inference doesn't scale. A more intelligent way to do this computation is by factorization and eliminating variables one at a time. We can first factorize the joint probability into two parts. One part contains factors dependent on Z0, and the other part contains factors independent of Z0. We can then push the summation over Z0 inside. And now we examine the inner product again, this time factorizing it over Z1 and push the summation over Z1 inside. And we do this factorization and rearrangement for all latent variables. The product inside each summation contains two free variables. So we need to compute a probability table of 4 rows for each summation. The overall computation is now decomposed into memorizable subproblems, and the time complexity is therefore linear in the problem size. Such an algorithm is known as variable elimination in the land of probabilistic graphical models. Now, what does this tell us about compiling probabilistic programs? In Maple, factorization takes the form of program partitioning. To eliminate a variable, say Z0, the program can be split into two partitions. One partition's probabilistic set effect depend on Z0, and the other partition's effect do not. The first partition's effect can be compiled away, giving rise to a pure expression that is a sum over Z0. And the original program is then transformed by combining the pure expression with the second partition. The resulting program is then partitioned again, this time over Z1, and the compiler eliminates Z1, compiling relevant probabilistic computations into pure expressions, and this process repeats until all variables have been eliminated, at which point we have a pure program. This pure program recovers the desired linear time computation. And the question is then, how does the compiler know which term goes to which partition? And our answer is information flow typing. Information flow typing is an end-to-end mechanism for program dependence analysis. We adapt this idea to probabilistic programs. To eliminate Z0, the compiler labels it high. The requirement is that high information not flow into low information, while low information can flow freely. Here, the compiler infers the typing for all the variables and terms. Terms typed high go to the high partition, and those typed low go to the low partition. Information in Z0 does not flow into the low partition. It is worth looking at the variable binding Z1 in detail. It may be surprising that the right-hand side term is typed high, whereas the left-hand side variable Z1 is low. Doesn't information flow from the right to the left? The answer is yes and no. It's a yes because information does flow from the right-hand side term to the distribution Z1 is drawn from. It's a no because, as we will see, the value of Z1 in a given execution trace contributes zero information to the semantics of the program. This design of the type system is crucial for program partitioning because otherwise all the latent variables, Z1, Z2, and so forth, would be labeled high, causing the entire program to be partitioned to high. One way to look at this design is that in Maple, the meaning of a term represented by a distribution over the values the term computes. And so the information flow label of the term classifies the distribution. Consider the typing rule for a variable binding construct. It binds x to T1 in T2. We can contrast it with a Euro information flow type system. What is un-Euro about Maple is that the left-hand side variable x is allowed to be at low, even when the right-hand side term T1 is at high. But why is that? The distribution denoting the composed term is obtained by marginalizing x out with respect to the distribution denoting T1. So this distribution denoting the composed term contains at least as much information as these two terms being composed. That's why in the conclusion of the typing rule, T1's label L1 is conjoined with T2's label. The label of x doesn't matter really. What matters is that the information contained in T1 is tracked in the type of the composed term. This suggests that we can safely type x at low without sacrificing soundness. We prove a soundness theorem for information flow typing. Soundness means non-interference. In the context of probabilistic programs, we interpret non-interference to mean low-labeled computation behaves irrespective of high-labeled input, measure-theoretically. We prove this non-interference theorem using a logical relations argument. Up to this point, we have been working with the straight-line programs. We also wanted to compile functions like HMM, which uses branching and recursion. We compile them in continuation pathing style. The compiled function takes an extra argument k. K is not the entire continuation. K is the portion of the continuation that the function returns value flows to. It's a pure computation. It represents the probabilistic effect performed by that partition of the continuation. The function body is then transformed with the continuation k, which amounts to compiling the two branches with k. The empty list branch is immediately turned into a pure expression. For the other branch, further translation is needed. We first eliminate variable z. We split the computation into two partitions over z using information flow typing. The high partition is turned into a pure expression. Now we eliminate y, which is the result of a recursive call. So we need to apply information typing to split the continuation of the function call. In this case, we only have a high partition, and the low partition is empty. We create a continuation argument k prime with this high partition, rearrange this computation, and pass k prime to the recursive function call. Now, all probabilistic side effects have been eliminated, and we obtain the pure function as desired. This pure computation computes the marginal likelihood of the original probabilistic computation. We prove that the compilation is correct with respect to this notion of semantic preservation. The theorem is a consequence of the non-interference property of the information flow type system. Now that compilation is proved correct, we assess if compilation and inference scale. For compilation time, we compare SlickStan and Maple. SlickStan is a state-of-the-art approach to variable elimination. It is designed for the STAN PPL. It enables STAN programs to have discrete latent variables. We use a hidden Markov model as a benchmark. This is a non-recursive program, as SlickStan does not support recursion. So the program size increases as the problem size increases. And as a result, we observe compilation time increases as problem size increases for both SlickStan and Maple, although Maple's compilation time is much less extravagant. Maple can additionally handle the recursive HMM. The program size does not change with the problem size. So Maple's compilation time scales perfectly. For exact inference, we compare Purple and Maple. Purple features exact inference for recursive programs. We use HMM and also a probabilistic context-free grammar as benchmarks. We observe that Maple is able to recover the polynomial time dynamic programming algorithms invented for such models. Variable elimination is an exact inference method. We can combine it with approximate inference to tackle programs that contains both discrete and continuous variables. By eliminating discrete variables, the Maple compiler reduces the dimension of latent space and may even decompose it into very low dimensional subproblems that can be easily solved by approximate inference. We mentioned two limitations of Maple. First, it supports recursion, but recursion must always terminate. This is in contrast to purple, which supports non-terminating programs. Second, Maple exploits the topological structure of a model, but not its local structure. This is contrast to dice, which taps into a program's local structure. Addressing these limitations is interesting directions for future research. To conclude, we have presented a compiler for Maple that uses information flow typing for variable elimination. And the payoff is that Maple allows useful recursive models to be expressed in a functional and recursive style, while enabling sound and scalable inference for a broad class of these programs. And thank you so much for your attention.
All right, thank you very much. We have time for a few questions.
Thanks for the really great talk. When you were mentioning the recursion must always terminate, does that mean it has to terminate in every possible path, or are almost always terminating programs okay?
Unfortunately, it has to be terminating all possible executions.
Cool. And can you give some intuition for what goes wrong in the, right, is it just that you end up needing infinite sums, essentially, in the unbounded case?
Yeah, exactly the case. Okay. So our compiler doesn't crash. It still compiles to a pure program, and that pure program makes unbounded, non-terminating recursive function calls.
Got it. Thanks. Can I ask one other
Go
question?
Ahead.
In the case of sort of partially compiling away discrete variables from continuous programs, what does the type of your translation look like in that case? You still compile to a probabilistic program?
Pardon, what's your question? Eliminating continuous variables?
Or you showed a slide about taking a program with both discrete and continuous variables and eliminating some of the discrete variables.
Yeah.
Right? So does your program transformation in that case compile a probabilistic program to another probabilistic program rather than to a pure program?
So in this talk, we don't have in the motivating example, this HMM program.
Yes, there's no continuous. Was that future work, the slide about the LDA and?
Actually, we can. Yeah, I think this slide is the best place to talk about this issue. So we do have some other benchmarks that contains continuous latent variables, and we can also, and the factorization splitting information flow typing also works for continuous ones. It's just they are eliminated. The subproblem for these continuous subproblems are solved in a different way. And here we can use, it depends on the problem. We can use important sampling, AAIS, or other approximate inference method to solve that continuous subproblem.
But does the transformed program contain those algorithms in it, or how does that work?
Yeah, the compiled program do contains a slice of probabilistic computation as a subprogram.
Cool. Thank you.
Thanks.
All right, thanks. Let's thank our speaker again.